Okay, so we've just finished talking about what happens to the filtrate we talked about the renal corpuscle. It goes in there, it's been filtered. There's filtration's going on there. So we've got filtrate. All the stuff comes out, it's in the filtrate. Then it enters the proximal convoluted tubule where 70% of all that stuff that was filtered out has now been reabsorbed back into the bloodstream. And then it entered the descending loop of Henle, where it lost water. So water came out, and water went into the blood and into the interstitial space. And then it curved around and it lost water till it got so concentrated. It was like a 1200 milliosmol, number there. And then it did the hairpin turn, came back up the ascending loop of Henle, and then we lost or got pumped out solutes into the interstitial space and back into the blood. So by the time it gets up to the distal convoluted tubule, the osmolarity is about 100. So it's pretty dilute. So it's entering the distal convoluted tubule, and if you remember, we kind of talked about the whole, renin, angiotensin mechanism there, and that's because there were cells along the distal convoluted tubule that monitor the filtrate for salt or content, whatever. So in the distal convoluted tubule, where it is monitoring the filtrate, it's monitoring the filtrate in order to aid in maintaining homeostatic balance basically in the body. And that balance is tweaked within the distal convoluted tubule and the collecting duct. And it does this through the function of hormones on it, okay? So one of the things it does is it monitors, or it helps the hypothalamus monitor and handle the osmolarity of the extracellular fluid, because the osmolarity of the extracellular fluid has an effect on blood pressure. So how does the hypothalamus do this? So I've got a hypothalamus here, and the hypothalamus has vessels in it that help to monitor the osmolarity and ultimately monitoring blood pressure. So it's not like the hypothalamus has some kind of a dipstick and it dips it into the blood and, oh, the osmolarity is whatever milliosmoles, blah, blah, oh, I better do something. No, can't really do that. So it has to do it another way. And so I've drawn here, we've got the hypothalamus here, and within it are these vessels. So it looks like there's two vessels here, but this is really the same vessel in two different scenarios. Okay. So the first scenario we're looking at is going to be where this vessel is at a osmolarity of about 270 milliosmoles. And the second way that we're going to look at this vessel is when it is at 310 milliosmoles. So normal osmolarity is about 280. Okay, so that means 270 is going to be below normal and 310 is going to be above normal. So what does that mean in the vessel? So basically, we're talking about the concentration of the stuff that's in the vessel. So at a low milliosmol, at a low osmolarity of the ECF, there's going to be less particles. So less stuff, less solutes, less particles. So if there's less particles, then there must be more fluid. So there's going to be increased volume, okay? More fluid. Say more water, okay? So in this scenario, the volume is increased. Okay. Okay. In this other vessel picture, we're at 310 milliosmoles. So that means there's more particles. So that means there's going to be less water. So decreased volume. So less water. Okay? All right. So, and we'll put that on here. It's got decreased volume in here. All right. So, what does that mean exactly, and why do we care, and what happens with the hypothalamus? Okay. Well, if we have more water in a vessel, more fluid, that means it's going to put more pressure on the walls of that vessel, and it's going to stretch those walls. So on these vessels are little receptors called stretch receptors. They're osmoreceptors, and these are stretch receptors. Okay? So these are mechanoreceptors. That respond to stretch. And it's going to be on both. I mean, obviously, let's do it on the other side here. Okay, so these are my little stretch receptors. So the hypothalamus is going to have nerves that are linked to these stretch receptors. Okay, and so in the first scenario, where we're at 270 milliosmoles, we have less particles and more volume. Okay, so what is this? What's going to be felt here? Well, you should be saying that it's going to feel stretch because we've got more volume, we've got more water in there, and it's pressing on the walls of this vessel. So it's going to feel the stretch, and the stretch is going to detect that volume. Okay? All right. So if there's stretch here, what's going to happen here at the neuron? Okay? Well, what's going to happen is there's going to be no action potential. Okay? Because osmolarity is maybe not fine, it's 270, normal's 280, but we have blood pressure. We're feeling the stretch. Okay? So hypothalamus does not do anything at this moment. There's no action potential here. It's feeling the stretch. Okay? So in the second scenario, we're feeling what? We're feeling no stretch. Why? Because volume is down. There's less water here, so there's only stuff in there and not as much water, so there's not any push or pressure on the walls of the vessel. So in that case, what's going to occur? Well, what's going to occur is an action potential. An action potential here, okay, at the hypothalamus. So if the hypothalamus perceives there is no stretch there, so hypothalamus perceives no stretch, what's going to happen? It's going to tell the posterior pituitary to secrete ADH, or vasopressin. Okay, so we know that's a hormone. What is the target of that hormone? Okay, well, the target of the hormone is the kidney tubules. Okay, so we need to reabsorb water. We need to bring water back into the body so that we can increase the amount of fluid or water in the vessels. Okay, so that the hypothalamus again is going to tell posterior pituitary, is going to secrete ADH, also called vasopressin, and that's going to target the kidney. All right, so let's talk about what happens when ADH targets the kidney.